Hello everyone and welcome to my presentation for the ESIAM 21 conference. My name is Alexander Berndt and I'm a researcher at the Carinthia University of Applied Science, and I'm going to talk today about our research on additive manufacturing of continuous carbon fiber tubes and experimental investigation of the energy absorption capability under quasi-static loading. My presentation starts with a short outline. I start with an introduction onto our take on FDM printing, moving on to our specimen design for the crash tubes, then the actual manufacturing and the multi-axis printing of these crash tubes. After that, coming to the quasi-static testing of the tubes, following the results. Last but not least, I'm going to talk about the conclusion of the testing and the outlook. Let's start with the introduction. Conventional 3D printing, also called fused deposition modeling (FDM) or fused filament fabrication (FFF), is a process of material extrusion of one or multiple materials. It's a layer-wise fused setup of this printed component. Novel materials such as continuous carbon fiber materials are used heavily in the field of aerospace, automotive, or medical engineering. The advantages of the fused deposition modeling process are easy scalability, high-speed building, and low costs. The disadvantages are the part quality due to the layer-wise setup of the component, the limitation in three-dimensional layer deposition, and the problem of force-dependent path design for fiber orientation. Based on the disadvantages of the fused deposition modeling process, we developed our ideas to enhance this process. We wanted to create a force-dependent path design for fiber orientation, develop our own printing strategies for high-performance composites, and use materials with a high energy absorption capability. In figure 2 on the right side, you can see a first schematic sketch of these tube-shaped objects we wanted to create, already with a force-dependent path design of continuous carbon fiber material. So we aimed on the implementation of a fourth axis, a modular setup of this fourth axis for easy use, and last but not least, the printing of these crash tubes. To design our specimen, we used the Aura software from Anisoprint. We created a layer-wise setup design of an alternating ply angle and 0-degree plies in between. It's a symmetrical stack in itself. We variated the ply angle from 15 up to 75 degrees and printed 25 test specimens in total. On the right side in the table, you can see the inner diameter of the tubes were 40 millimeters. The total number of layers is 8. The layer height is 0.125 millimeters, resulting in a wall thickness of 1 millimeter and an outer diameter of 42 millimeters. The printing properties were based on the material we used from Markforged. So we chose 270 degrees Celsius of printing temperature and a printing speed up to 30 millimeters per second. In figure 3, you can see a sliced 15-degree fiber angle layup of a crash tube specimen in the Aura software. The idea of our multi-axis printing is the adaptation of the conventional winding process of fiber-reinforced tubes. We wanted to build a modular fourth axis with a separate stepper motor for control. In figure 4, you can see the conventional winding process of fiber-reinforced tubes, and we choose to use the cylindrical axis of the winding process to use as our modular fourth axis. It is controlled by a stepper motor on the left, held by 2 bearing blocks, and all of this is built onto a platform. So our cylindrical axis becomes our new printing bed, which is already known by the conventional 3D printing. To demonstrate our modular axis, you can see the video, and at the moment the first layer of the 30-degree fiber angle is printed. Now the second layer, of the 30-degree fiber angle is printed. And after that, the first 0-degree ply is also printed onto the already existing ply layers. The video is sped up, so the process itself takes way longer than shown here. For conducting our quasi-static testing, we used our Zwick Roll Z020 universal testing machine. The crash tubes had an initial length of 100 millimeters, and for damage triggering, we chamfered our crash tubes in a 45-degree angle. Before crushing the continuous carbon fiber tubes, their initial weight was measured. Tubes were then compressed at a speed of 10 millimeters per minute for a total crosshead displacement of 80 millimeters. The values of force and displacement were recorded to examine the energy absorption capability. A force displacement diagram was created from the data. On the right side, you can see the quasi-static testing of a CCF tube with 30-degree fiber angle. It is sped up by 20 times. As you can see, the circumferential delamination starts and small petals are created during the process of compression. The efficiency of the crash tube during the quasi-static compression test is determined by the crush force efficiency. This is the ratio between the average crushing force and the maximum crushing force. The specific energy absorption capability is determined by calculating the average load over the crush distance per absorbed mass of material. On the right side in figure 5, you can see progressively crushed cylindrical composites. In figure A, you can see the axial cracks initiated by the quasi-static compression testing and the circumferential delamination. In figure B, you also can see the petals which are formed by compressing the tube. The quasi-static compression tests were performed on each set of specimens. Figure 6 exemplary shows the crush behavior of one continuous carbon fiber crash tube with a 60-degree fiber angle. In the first two pictures, you can see the start of the damage triggering process until shortly after the elastic region. In the last three pictures, figure C to E, the progressively crushed continuous carbon fiber crash tube is shown. Due to the chamfering of the specimen, a local failure is initiated at the start of the crushing process. This leads to a circumferential delamination and axial cracks, and therefore petals are formed. After bending the petals even further, the petals will fracture caused by the brittle behavior of the carbon fiber. The results of the quasi-static compression testing are shown in the diagram on the right. The diagram shows the force displacement curve of one specimen of each set. The data was chosen based on the best crush force efficiency value of each specimen set. The best specimen with a fiber degree angle of 15 degree has a crush force efficiency value of 0.83. The table on the left shows the average values of maximum force, the average of the average force, the average of the crush force efficiency, and the average of the specific energy absorption of each set. The first set with a 15-degree fiber angle layup has the best crush force efficiency, whereas the set with a 75-degree setup has the lowest average specific energy absorption value. despite the fact that one of the specimens withstood a maximum force of up to 20 kilonewtons. That the 15-degree fiber stack-up has the highest specific energy absorption can be explained by the basics of composite materials, where if the loads are applied parallel to the fiber direction, the fiber can absorb less energy compared to a perpendicular fiber angle. This diagram summarizes the specific energy absorption average values obtained for all sets of specimen. It shows that the 15-degree fiber stack-up has the highest specific energy absorption capability. As explained earlier, it is explained by the basics of composite materials. To conclude this study, it was shown that a modular fourth axis was implemented into an existing 3D printer, and the possibility of printing on the fourth axis has been shown also. 25 crash tube specimens were printed successfully, and the optical analysis exceeded our expectations. Although CT scans are necessary for a better qualitative analysis. Furthermore, the energy absorption capability of different fiber-aligned continuous carbon fiber crash tubes has been determined, and it was shown that the 15-degree fiber stack-up was the best. Further research needs to go into the specifics of petal forming and the adhesion between each layer. This means that not only a low directional design of the continuous carbon fiber tubes is useful, but also regarding crack propagation and fatigue behavior needs to be taken into consideration. If there are any questions, don't hesitate to ask, and thank you for your attention. Bye.